So, all right, so here we have a function, x squared plus 1. It's a nice parabola. Vertex at the point 0, 1. You know, we could find the focus and stuff if we wanted to, but, you know, we're going to answer a slightly different question. You know, what we did last week or the week before was sort of connecting ideas about the behavior of a function, what its graph looks like, connecting it to what its equation looks like. And in calculus, we do that a lot. We do a lot of analysis of functions. And so one way to describe this function is to describe how it changes, right? I mean, you know, we have different kinds of functions. You have a constant function, doesn't change at all, right? It's like a horizontal line. And we have like linear functions, and those change with a constant slope, right? With those very predictable ways in which that changes. And then we have a function kind of like this, and you know, the way it changes, right? Like first it's decreasing, and then it kind of levels off, and then it's increasing. And what we want to do is kind of figure out a way to describe that mathematically. And we're going to do this by trying to describe how it changes at a particular point. There's nothing special about this particular point, but we're just going to pick the point 2, 5. So if x is 2, then y is 5 in this function. And so here's that point on the graph. And we're going to try to describe how it changes just at that one point, which means what we're going to do is draw a line. We call it a tangent line. A tangent line is a line that touches a curve at just one point. So it kind of like just like brushes up against or like kisses that curve right there. And the way that function is changing, the behavior of that function, or how it changes at that point, could be described by finding the slope of that line. Clearly, it's increasing. I mean, we can see the curve is increasing anyway, right? The function's increasing. And at this one point, if I could find the slope of this one point, then that would be like how it's changing right then. That won't be how it changes down here or down here. In fact, there's some points where we can kind of see how it's changing numerically, like see exactly what the slope is without doing much work. There aren't too many of those points, but like right here at the bottom, if I draw that tangent line, what kind of line is it? It's horizontal, right? Like, and its slope is 0. So like there are these places where the curve kind of levels off, and it doesn't require much at all for us to figure out what that slope is. That's going to take a little bit of doing. And the reason is because usually if we want to find the slope of a line, we need 2 points. We have 1 point. So here's what we're going to do. We're going to choose a different line to look at first. So this I've just zoomed in on the same curve in the first quadrant. So here's the point 2, 5. I'm going to call this point P. And I'm going to make a different line, and the way I'm going to make that different line is I'm going to pick another point on the curve. I'll call this point Q. Now, I'm being arbitrary about it, so I haven't picked a particular point Q. So it has some arbitrary x coordinate. And if I know the x coordinate, then its y coordinate, I know what the y coordinate is in terms of x, because this is the curve, y equals x squared plus 1. So this has coordinates x and x squared plus 1. All right, so there's another point. And I could be specific about that point. I could pick x equals 3 or 2.5 or 2.1 or something, right? And if I did that, I could find the actual numerical slope of that line. And it wouldn't be the slope I'm after, right? But it's a way to kind of get around the problem of having just 1 point. So what I want to do now is say, let's not fix that point. Let's keep it as x and x squared plus 1. And if I were to find that slope, I'll call this MPQ because I'm finding the slope of this line. This line, by the way, we call it a secant line if there are 2 points on the curve. Instead of a tangent line, we call it a secant line. We're going to find an expression that will give us the slope of that secant line. And we can do it, right? Rise over run. So difference in y's over difference in x's. So the numerator would be, what, x squared plus 1 minus 5 over x minus 2. We can simplify x squared minus 4 over x minus 2. So now no matter if I were to actually fix that point Q, pick any particular x coordinate, I just plug in the x coordinate there into that expression, and I'll know what the slope of the secant line is. Still, that would just really give me an approximation of the slope of the tangent line. Like, it's not the line, it's not specifically the line we want, but what we're going to do to get that tangent line, we do have the difference of 2 squares there, and that's going to be useful. What we want to do in order to get the actual tangent line is just imagine that this point Q is like a free point that can slide along the curve. I can slide it up and down. And what I'm going to do is push Q closer and closer to P. Ideally until it's the same point as P, right? As soon as, if Q becomes P, then that is the tangent line. So we have a way to do that in mathematics. We're just going to take a limit. We're going to let Q approach P, and then evaluate what are those secant slopes approaching as Q approaches P. So let's set that up. And here's where it will be particularly helpful to observe that we have a difference of squares up there. So this tangent slope, which I'm going to call m tan, is the limit. I'm going to write it this way first, as as Q approaches P of the slope MPQ, right? Like, sort of physically, that's what we want. We want to push that point Q so it's getting closer and closer to P. But as Q approaches P up here, that means that this x coordinate has to approach 2. So this is going to be the same. This limit as Q approaches P is the limit as x approaches 2 of this secant slope expression. So as Adam pointed out a couple minutes ago, we have a difference of squares up there. Here's the limit, like a limit like we might have, computed last week. I can't let x approach 2, right? Letting x equal 2 is a problem right now. But we could do some algebra and see if we can't eliminate that problem. So we have x plus 2, x minus 2 over x minus 2, and these x minus 2's cancel, and now all of a sudden it is no longer a problem to let x approach 2, right? In that expression we can let x be 2, no problem. And so if we let x equal 2, then we get a slope of 4, and there is the tangent slope. That's the slope of the line tangent to the curve at that point. Notice I carried the limb part through the whole way, and that's really crucial because these two expressions, like x squared minus 4 over x minus 2 and x plus 2, they are equivalent expressions almost everywhere, right? But the one place that they're not the same is precisely the place that we're interested in finding it. And that's why in order to make sure we're writing down things that are true, we have to carry that limb through. And it's only when we let x approach 2 that we drop that limb.
So that's saying that that secant line is, the slope of that is 4?
No, it's saying that the slope of the tangent line is 4. Right?
We just use the point in order to get find that?
Yeah. Like this, that's the slope of this line. That's the tangent line. So what we did was we said, we took this point Q, that exists on the curve, and we kind of slide it closer and closer. We pushed it closer and closer to P. And as you push this point Q closer and closer to P, the slope of the secant line, the one in black, kind of pivots a little bit along, right? It's fixed here. It's always on this point. But that slope kind of pivots a bit until it becomes this red line, that tangent line. And that's the slope that we found, the slope of the tangent line. pretty exciting, yeah.
So, I mean, when you look at a line, you can kind of like guess what the slope is just by looking at it. Like you can visualize what it might look like.
Right.
So like that, to me, doesn't look like a slope of 4.
Well, look at the...
Up 4 over 1, like that doesn't
Yeah,
really
but look at the different scales.
Yeah. Oh, I see.
Yeah. Okay, are you ready for some more? Now there are certain things we can tell just by looking at the graph, right? You said like we could kind of tell maybe what the slope is. So this slope of a tangent line, if I look at like the full, you know, the whole thing, I know that if I find the slope of a tangent line over here, I'm going to expect it to be negative, right? And it's going to remain negative. Now, but if I compare this point to this point, I'm going to expect this to be a bigger negative number than this point. Right, like as I kind of trace and I keep drawing these tangent lines, you know, like this, they both have a negative slope here, but like down here it kind of starts to level off, right? Down here I could see, oh, that looks like it's probably going to have a slope of 0 at that minimum. And then, you know, kind of changes, turns upward. For points up here, still positive, but I'm going to expect that slope to be bigger than this slope here. So we're going to generalize this now. And let's say here's just a general, there's nothing specific, there's no equation of this curve, that's just like an arbitrary curve that I drew. I do have to make one correction here, because this point Q, the x-coordinate should be x plus h, which makes, of course, the y-coordinate f of x plus h. So this idea of taking a point, you know, we have this one point that we're interested in looking at, and then we kind of sneak up on that tangent slope by grabbing another point that's arbitrarily chosen and sliding it closer and closer. We're going to generalize that, and the reason that we're going to do that is because this was great and all to find the slope at x equals 2, but like, what if I also wanted the slope at 1 and at 1/2 and at -3? You know, I have to like kind of go through and set up that limit again, and that's fine. But what we're going to do on this page, and what's sort of presented to us, is a way that we can get the slope at an arbitrary point, so that by the time I'm done evaluating this limit once, what I would get is an expression with x's. So that expression will just give me what the tangent slope is at any point. So one limit takes care of the whole function, no matter what point I'm interested in. And so the way we do that is we say, okay, let's say we're interested in the slope of the line that's tangent at this point, P, and now this point is arbitrary, x, and then its y-coordinate is f of x. The way I'm going to get that other point, Q, that I wanted, is I'm going to say, let's just move up a little bit. And I'm going to move up by some amount I'm calling h here. In our textbook, they call it delta x for change in x. So you make a little note there. You're going to see that notation a bunch in the text. So now if I find the slope of this line that's in blue, this secant line, I've got f of x plus h minus f of x, there's our change in y's, over x plus h minus x. And if I find, you know, in the denominator, x plus h minus x is just h, right? It's like there's our change in x's is h right here. And now if I want to slide that point Q closer to point P, the way I do that is I let h approach 0. So that's why if we find the tangent slope is going to be the limit as h approaches 0 of that fraction, f of x plus h minus f of x all over h. We're going to do a bunch of problems today where we're finding tangent slopes, and we're going to start out and I'm going to write that limit fresh every single time, even though we just wrote it down in the last 2 or 3 examples. And I'm going to do it because that's something that you're going to need to commit to memory, and it'll be virtually impossible for you not to know it after you've written it down about 200 times. You're going to see it when you go to bed. You're going to dream about it, okay? So this tangent slope, just as a quick note, we also refer to it as an instantaneous rate of change of f of x, of a function. So it's like how it's changing at this particular point right here. right? Because the nature of these functions, right, the way they changes, right? Like sometimes they're decreasing, sometimes they're increasing very quickly, and sometimes very slowly. So when we want to figure out how it's changing right at this one moment, that's an instantaneous rate of change. The slope of a secant line would be like an average rate of change. That's sort of like if I drive from here to home, I could say how long it took me, versus what the total distance is. If I do some division, I can find my average velocity, but that does not tell me how fast I was driving at any particular point along the road. So there's like the difference between an instantaneous rate of change and an average rate of change. Okay, so we're going to use that new limit on the previous page to find an expression for the slope of the line tangent to the curve y equals 4x minus x squared at the arbitrary point xy. So what we're going to do is we're going to set this limit. What we're going to end up with is a formula that has x's in it that will tell us, like, I could find the slope tangent at any point by just plugging an x to that result that we get. So let's begin. This limit that we need, the limit as h approaches 0, f of x plus h minus f of x all over h. So I know what f of x is. Let's do a little side work, figure out what f of x plus h is. What does it mean to find f of x plus h? What is it that we want? Well, yeah, I mean, the h is the change in x, but like, how do I get an expression for f of x plus h? I guess maybe it's the same question as, like, what if I wanted f of 2 or f of 3?
Sub in x plus h.
Yeah, right. So we're going to sub in x plus h for x in the formula, in the function. Do a little algebra. Let's expand this out. Let's see, x squared plus 2xh plus h squared, and then distribute that negative. So there's f of x plus h. If I wanted f of x plus h minus f of x, which is, of course, precisely what we want, then we'll just subtract f of x. And if I subtract f of x, that means I'm going to subtract 4x, and I'm going to add x squared. I'm going to pause there for a moment and see if that's okay. Like, does that make sense? So if I want to subtract f of x from f of x plus h, so I'm subtracting f of x. And if I subtract f of x, that means I'm going to subtract 4x and I'm going to add x squared. Right, because I'm subtracting a negative x squared. So I've just written that down this way. Like I've done, here, let me write, like what I've done is minus f of x is the same as minus 4x minus x squared. And if you distribute the negative, right, that means I'm subtracting the 4x and then I'm adding x squared.
So you just got the right side of it to the point of f of x plus h, and then you did that.
Yeah, like I've done the same operation on both sides.
Yeah.
Right, I subtracted f of x here and I subtracted f of x here. I've just written it down. I just used the function notation here.
So that's the entire numerator is 4h minus 2xh minus h squared.
Say that again. What's the numerator?
4h minus 2xh minus h squared.
Yeah, so you just did the subtraction, right? Because these cancel out, right? So f of x plus h minus f of x is equal to 4h minus 2xh minus h squared. Yeah, that is precisely correct.
You can pull an h out.
We can, and we will. I'm going to kind of go back here to our limit. and write this out first. We want to let h approach 0, and so of course initially we can't do that, right? Like that's a problem. We can't divide by 0. But notice that when we did this subtraction, every term has a factor of h in it. When the function that you're working with is a polynomial, that will always, always happen. If I find f of x plus h minus f of x and I'm working with a polynomial and I end up with some terms that don't have an h in it, that means that there's an algebra mistake I made somewhere and I need to go find it and fix it. So we can pull out that factor of h. And of course, we do this in order to cancel. Our goal, intermediate goal, is to like get rid of that h in the bottom. Like we want to be able to let h approach 0. So we get this expression when we're done with working out the algebra. We could factor out an h. Now that we've done that, we can totally let h approach 0. Now, as h approaches 0, nothing's happening to 4, right? Nothing's happening to that 2x, right? There's no h's there. So as h approaches 0, that just means this guy approaches 0, goes away. And the expression that we end up with is 4 minus 2x. And that is our tangent slope as a function of x. So we had to do some algebra, but we have to, we worked out this one limit. Then the problem continues and asks us to find the slope of the line tangent when x is -1, when x is 2, and when x is 3. I don't have to do 3 limits for that. I've got this one limit here. So when x is -1, the tangent slope is 4 minus 2 times -1, or 6. At x equals 2, the tangent slope is 4 minus 2 times 2, or 0. And when x is 3, the tangent slope is 4 minus 2 times 3, or -2. We didn't have to do new limits each time. What is it? I mean, do we get any insight or predictions, or like, I'm going to pull up a graph of this in a minute, but before we look at a graph of this function, what do you think we're going to see at the point, like what kind of behavior do you think we're going to see at the point x equals -1? Given that, yeah, it's going to, in what direction? Positive, right? It's going to be increasing. What do we expect to see at x equals 2? It's going to level off. And what about when x is 3? Decreasing. Probably not as steep as it was increasing over here, right? But like still decreasing. So let's look at that. Then to set my window. Let's say I'll go from like -5 to 5. Okay, so at x equals -1, we're over here. Definitely pretty positive. It's increasing pretty sharply. Here we are at x equals 2, corresponds to where it levels off, the nose of this parabola. And at x equals 3 is definitely decreasing there.
Yeah, doesn't it seem like it would be a positive or a -6? It almost seems like it would be the same.
Really? at -1?
Oh, no.
Oh, you mean like over here?
Distinctness.
Yeah. Well, like here at -1, like it's
Oh,
like
okay.
almost off the graph actually.
Yeah.
So and then here it does seem not quite as steep.
No, I
Yeah. Yep.
I didn't realize that the crossover to 4.
Yeah.
So you're using that f of x plus h because you know it's the arbitrary point, as in it's
Right. It's sort of how we obtained the other point, right? Like over here, so we're interested in the tangent slope here for the point P, and we need to get that second point, and because this one's arbitrary, I can't just call that one x. But the way we obtain that other point is we say let's just move up a little bit by amount I'm calling h, and so in order to let this point get close to P, I just need to let h get close to 0. Like let that amount, that I move up be like just get closer and closer to 0. And then that secant slope will get closer and closer to the tangent slope. Other questions?
So if your arbitrary point was to the left, would it just be a y equals some negative?
Well, you could pick the arbitrary point to the left, and it would be like maybe x minus h,
Gotcha.
right?
Yeah.
But you have to be careful because if you're letting h approach 0, like when you make that, if you set it up so it's x minus h, then up here it's a little bit different. So it'd be x minus h minus f of x, like as we would expect. But then when you do the change in x's, it's x it's x minus h minus x, so it's actually negative h that ends up in the bottom. So like I always treat it as like an x plus h because it can be easy to make a sign error, but it's totally valid. Like you can do it, like it'll work, but it ends up being a negative h on the bottom, and if you didn't make that change, your answers would be reversed. How we doing? Ready for more? Okay. So let's do the same thing for this function. We're going to find the expression that will give us the slope of a tangent line at an arbitrary point, and then we'll use it to find that slope when x is a half. So our function, f of x, is x cubed plus 2. So f of x plus h is x plus h all cubed plus 2. So we got to cube out that x plus h. There's going to be times when you might have to take x plus h and raise it to the 4th power, or maybe the 5th power, right? There's a lot of algebra. If I were to kind of do it out manually, right, just think about foiling and stuff, I'd have x plus h times x plus h. I'd do that first, right, and then take that expression and multiply it by x plus h. You might recall, like sometimes I like to draw that little grid, that table, right, kind of organize the multiplication. But that is very enjoyable to do. I really like it. But there's like a more efficient way to raise this to the 3rd power, or the 4th power, or the 5th power. So I'm going to I'll go off on a little bit of, it's not really a tangent, pun intended, because it's very much related and will be useful to what we're doing. So if I wanted to cube out x plus h, I know I'm going to have an x cubed term. Maybe I don't know what the coefficient is. I know I'm going to have like an x squared times h term. I know I'm going to have an x times h squared term. I know I'm going to have an h cubed term. And this is how it will always work. You can start out with like all x's, right? These are the x's being cubed. All x's, no h's. And then you kind of step down the powers on x, 2, 1, 0, as you increase the powers on h, right? 0, 1, 2, 3. For each term, when you add up the exponents, you get 3. You get that guy. The only thing we don't know are what these coefficients are. So this is where we're going to use Pascal's triangle. So Pascal's triangle starts this way, and we can always recreate it. So it starts with a 1, and then a 1 and a 1. Each row starts with a 1, and then to get it, the next entry, you add the 2 above it. So there's a 2, and it ends with a 1. I start with a 1. That's a 3. That's a 3. That's a 1. What do you think this next row is?
1, 4, 6, 4, 1.
Mm-hmm. And the next one?
1, 5, 10, 5, 1.
Yeah. Right? We could go on infinitely. Yeah. So, fun, right? So now, this is, we wanted to find x plus h cubed. Our coefficients are going to come from the row that begins 1, 3. So, 1, 3, 3, 1.
How do you know? Oh, the one that has 3s in it?
Yeah, it's so the top row of Pascal's triangle, we call that row 0, and then there's row 1, row 2, row 3, row 4. So like row n is the row that begins 1n, right? And if I'm cubing it, right, whatever this power is, that's the row I'm going to use. And you should be able to detect if you pick the wrong row anyway, because it might not have the right number of values, right? Like so if I wanted to find, for fun, right, if I want to find x plus h to the 4th. Well, I'm going to start out by saying, okay, what are my terms that I'm going to have? You know, I know I'm going to have an x to the 4th term. What's my next term?
X cubed h.
X cubed h,
X squared.
x squared, h squared,
H to the 4th.
well, eventually, yes.
X h to the 3rd.
X h to the 3rd, yep. And then x to the 4th, or h to the 4th. So I start with all x's, and then these powers on the x's decrease as the powers on the h increase. You can sort of see the powers on x kind of being walked down as the powers on h are being walked up. What are my coefficients going to be?
1, 4, 6, 4, 1.
Yeah, Pascal's
Wow,
triangle.
yeah, the subtraction.
So if you have a subtraction, that's a really good question. If you have a subtraction, the signs end up alternating. So you'll end up with a plus. It starts positive. Like if it was x minus h to the 4th. The signs alternate, and the reason is because, so it'd be a minus 4x cubed h plus 6x squared h squared minus 4xh cubed plus h to the 4th. So it ends up alternating, and the reason is because I see that x minus h as x plus a negative h. And so when I'm raising, the powers on h, I'm really changing the powers on negative h. And so if you take a negative and raise it to a negative power, you get a negative. Or sorry, if you take a negative and raise it to an odd power, you get a negative. Right? So like there's h to the 0 is positive. Or negative h to the 0 is a positive. Positive h to the 1st is a negative. Or negative h to the 1st is a negative. Negative h squared is a positive. Right? Negative h cubed is another negative. So that's why you get this alternating. For the most part, and maybe even for the entire part, like for our purposes and how we're seeing this and using this, x plus h is what we're going to see, and how we're going to set up that limit. Okay, so now let's return to that example. So x plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed plus 2. And so if I want to find f of x plus h minus f of x, so now I'm going to just subtract f of x. And if I subtract f of x, what I'm really doing is I'm subtracting x cubed and I'm subtracting 2. And the expression we're left with after stuff cancels is 3x squared h plus 3xh squared plus h cubed. At this point, I do my quick check because x cubed plus 2 is a polynomial. So I just do a quick check. Everything has a factor of h, and that's a good sign. Now we're going to set up the limit. So our tangent slope is equal to the limit as h approaches 0, f of x plus h minus f of x all over h I can't let h go to 0 because that makes us divide by 0. So what do we do?
Yeah.
Yeah, let's factor out the h. And then we cancel. This is what victory feels like.
So then it really just 3x, right? It's 0.
Yeah, so h is going to 0, right? So those last two terms diminish, right? These guys go to 0. So what are we left with? 3x squared. There's 3x squared. Yeah. So this is the expression that'll give us the slope of the tangent line at any point. Like as long as I know the x coordinate, I know what the slope of the tangent line is. They've asked us to find the slope of the line tangent at when x is a half. So 1/2 squared is a quarter. So we get 3/4. So it's increasing, not like crazy steep, but it's increasing there. What if I was interested in where this, like, does this function level off? If I looked at a graph of this function, would I expect to find that it levels off anywhere? And how could I figure that out before I look at a graph?
How would you get to the leveled off part?
Yeah.
Plug in x for the two values and see where they are related to each other. Like, well, how increasing one is or negative.
So like plug in two values to this?
Can you set it to 0?
Oh, set what to 0?
Let m tangent.
Uh-huh. Yeah,
And
why?
then find x,
Yeah, why?
because that's where it's going to be.
Where the tangent slope is 0, right? Any point where it levels off, like whether it's like kind of cresting and coming down or like hitting a trough and then coming back up, that tangent slope is going to be 0. So like if I want to detect a point like that, I can use this expression that we found for MCAN. So I know that there's only one place where this levels off. I don't even have to look at the graph. Like I know the only place we're going to have any leveling off behavior is at x equals 0, because that's the only thing that makes this 0. And as it turns out, it's kind of hard to detect, and we're gonna learn more about like exactly how we detect this and like how to do some more analysis. That leveling off doesn't happen at a crest or a trough in this case. It does one of these things where it's like that. So that's sort of like right here is where it's leveling off.
How did you identify that those were 0? Just as a side note, kind of backwards.
Oh, that in blue? Because we are letting h go to 0. And so any term that has a factor of h, yeah, it has to make sure that h is like a factor. So it wasn't something plus h, but it was something times h, right? So if that h is going to 0, then that whole term is going to 0. Other questions?